And team, you can start your presentation.
Can you guys tell me if you can tell me when you see my can you see?
Yeah.
Okay.
Yeah.
Okay. So good morning to one and all present here. I hope everyone had a good weekend. I'm going to get right into my topic as we don't have a lot of time. So after you hear any topic, the first thing you think is what it is, right? So what are numerical methods? Numerical methods is approximation, fast solution for mathematical problems. Such problems can be in any field in engineering. So any result you get from it is approximated and not exact. It gives you the solution faster than the normal ones. Also, it's easy to be programmed in softwares like MATLAB, for example. Here are some of the issues that numerical analysis is used in. Solving linear and nonlinear equations. Bisection, interruption. These methods we use to find real roots, and they fit some points to the curve, they're good approximation and simple solution. Interpolation, great to get any value between table of values. You can solve equally spaced readings for unequally spaced methods. Solving partial differential equations like Laplace equation, wave equation, and Poisson equations. We use methods like Bender-Schmidt, Crank-Nicolson, etc. Nextly, why are numerical methods important? Analytical solutions are exact solutions based on mathematical principles. However, the governing partial differential equations of fluid flow are complex and cannot be solved by analytical means. The partial differential equations are therefore converted into a system of algebraic equations that are subsequently solved through numerical methods to provide approximate solutions to the governing equations. Although we rarely reach an exact answer, we get really close to the exact answer much quicker than if we solved it analytically. As such, an important part of every numerical method is a proof that it works. So that there is the answer. We need numerical methods because a lot of problems are not analytically solvable, and we know that they work because each separate method comes packaged with the proof that it works. Now moving on, where do we use numerical methods? Numerical analysis, the area of mathematics and computer science that creates, analyzes, and implements algorithms for obtaining numerical solutions to problems involving continuous variables. Such problems arise throughout the natural sciences, social sciences, engineering, medicine, and business. Since the mid-20th century, the growth in power and availability of digital computers has led to an increasing use of realistic mathematical models in science and engineering. And numerical analysis of increasing sophistication is needed to solve these more detailed models of the world. So as you guys would have noticed, I would have said computer a lot of times. So that is what a team is going to present to you about today, computer architecture. And I'll give you a brief introduction on it. So computer architecture is a set of rules and methods that describe the functionality, organization, and implementation of computer systems. Some definitions of architecture define it as describing the capabilities and programming model of a computer, but not a particular implementation. In other definitions, computer architecture involves instruction set architecture design, microarchitecture design, logic design, and implementation. Next, my teammate Maharajan will talk to you about instruction set architecture.
Hey guys, good morning. This is Maharajan. We had a nice intro from Nishant about the computer architecture. So I'm here to explain you about the instruction set architecture. Next slide, please. Okay. First, we'll look about what is instruction set architecture. Nishant, can you move to the next slide? Yeah. So instruction set architecture basically means that it describes the design of a computer in terms of the basic operation it must support. The ISA is not concerned with the implementation specific details of a computer. It is only concerned about the set of basic operation that a computer must support. So if you take an example of the AMD Athlon and the Core 2 Duo processor that have entirely different implementation. Please stay with that slide. Just go to the.
Yeah.
So if you take the example of AMD Athlon and Core 2 Duo processors, they have entirely different implementation, but they support more or less the same set of basic operations as defined as in the x86 instruction set. You can go to the next slide. Okay. Now let's see an example of an instruction set architecture, which is MIPS, microprocessor without interlocked pipeline stages. Okay, it is a reduced instruction set computers, instruction set architecture. It's developed by MIPS Computer Systems. It's now known as MIPS Technologies, based in the United States. There are multiple versions of MIPS, including MIPS 1, 2, 3, 4, and 5, and they run on different versions, 32 bits and 64 bits. As you can see, like it's one of instruction sets developed really. You can go to the next slide. The types of instructions. When we say instruction set architecture, it has certain instructions that has to be followed by the processor. So arithmetic logic instructions. These instructions perform various arithmetic and logical operations on one or more operands. Data transfer instructions. These instructions are responsible for the transfer of instructions from memory to the processor, registers, and vice versa. Branch and jump instructions. These instructions are responsible for breaking the sequential flow of instructions and jumping to instructions at various other locations. This is necessary for the implementations of function and conditional statements. One more thing is that the ISA defines the maximum length of each type of instructions. So see, if you take MIPS as an example, it's a 32-bit ISA. Each instruction must be accommodated within the 32 bits. Okay, we can go to the next slide. We'll look about the instruction formats of each type of instructions. The instruction format, stay with instruction format. Okay, Nishant. The instruction format determines how the entire instruction is encoded within the 32 bits, as we're taking for MIPS as an example. So there are three types of instruction formats in the MIPS. Say R instruction format, I instruction, and J instruction format. Each of the above instruction formats have different instruction encoding schemes and hence needed to be interpreted differently by the processors. So, yeah, go to the next slide. Yeah. So now we look at the addressing modes. So what is addressing modes? Addressing modes refers to the way in which the operand of the instruction is specified. The addressing mode specifies a rule for interpreting or modifying the address fields of the instruction before the operand is actually executed. So if you look at an assembly language program, it consists of two parts: opcode, operand. The memory address of an operand consists of two components mainly. Okay, that is opcode and operand. So if you have addressing mode of 8086 instructions, they can be divided into two categories. One is addressing modes for data, another one is addressing mode for branch. So the 8086 memory addressing modes provide flexible access to memory, allowing you to easily access arrays, records, pointers, and other complex data types. The key to good assembly language programming is the proper use of memory addressing modes. So that's the importance of the addressing modes and what is addressing modes. Yeah, go to the next slide. The flow control. We all know about flow controls. Like it's the basics of some programming languages, and it is also the basics of operation OS as well. So operation systems. Flow control instructions are used to divert the flow of the program. If we know, right, the if else statements and those things. These instructions are used to implement loops and subroutine calls. Basic instruction is the branch, and the conditional affixes can be added to the branch instructions to enable choices. allow conditional execution of the codes when coupled with the status bit operation structures. That intro about
I'm Ajay. I'm going to explain about assembly language. As you know, in the olden generations, the first time when computer was created, it was mainly made for calculator purpose. So like the only purpose of that was like to do addition or subtraction. But now, like as you can see, the olden days computers were not multitask. They were nowadays we need the universal thing. That's why the invention of CPU, by the invention of CPU and by Alan Turing, you would have seen the movie Imitation Game. That Alan Turing, he cracks that enigma. By through that, we can use the algorithm and we can do many programs, like we can execute through the computer. The computers basically, it uses 1 and 0. 1 is like to complete the circuit and 0 is for that. So using that, we do many programs. So the only thing that the computer understands is machine code. As you can see, this is CPU. Like because of that only we are able to do many programs now. You can go to the next slide. Yeah, assembly language. As you can see in the right side in the picture, the machine code, like this machine code is for this. The basic code is I equal to 15, J equal to 10, and I equal to I plus J. But the computer can understand only in this machine code, as you can see in the right. So like to understand that, the first thing that was created was this assembly language. This assembly language is the human form through which we can type this code and we can do that. The assembler, as you can see in the photo, what it does is we as a humans can do it in the human form as assembly language. The assembler changes it to machine code. The function of assembler is to change it to machine code, and the computer can do that to machine. Computer can understand machine code and it will process. You can go to the next page. But even as you can see, the assembly language is like a little complicated, but it was the first language that it was created, so it's fine. But nowadays, if you can see, the whole code is, as you can see in the left, is just a 3-line code. But in the picture, if you see, the compiler changes the changes the advanced code like C, Java to assembly code. As you can see, the assembly code is some nine sentence code, but in the advanced languages, it's just 3-sentence code. So basically, the difference between the difference between compiler and assembler is compiler first changes the advanced level code to assembly code. It compiles and then it changes to machine code. So compiler does changing it to assembly code and to machine code. That's the thing. And like nowadays we use C and Java. Earlier they used to, and you can see like if you're creating a game in assembly language, it would be very lengthy. But in advanced languages, you can see that nine sentence has been changed to 3 sentences. That's a different. Next page, next slide. This is a short topic. The main things that you need to know in this topic are CPU. CPU is a broad topic on its own. The whole assembly language, the concept came because of the invention of CPU and by that algorithm system of Alan Turing. That will be covered in the next topic. In your worry if you didn't understand fully. Then the machine code. Machine code is the instructions that we use like to convey to the machine code is the language through which the computer understands us. And since that language is tough, we use assembler as a translator and we use assembly language. So you would understand the first 3. The assembler's job is mainly to change the assembly language to machine code. The machine code is the only thing that computer understands. And compiler, as you can see, it does the job of assembler first, but first it compiles it from high level language to assembly language. The first topic, CPU, is a broad topic on its own, and it will be covered by the next person, Abhishek.
Good morning, everyone. This is Abhishek over here. So I'm going to explain you about each and everything about the CPU. Nishan, please talk on this slide. So CPU, the abbreviation for the central processing unit, most commonly referred as a processor. You can refer it as the brain of each and every computers. In terms of computing power, the CPU is the most important element of a computer system, which converts the human language, or you can say the assembly language, into the machine language, or it allows the interaction between the humans and the machines. So in further, I will discuss about some of the important components of the CPU. Nishan, to the next slide. This is the block diagram of the CPU, of the basic CPU, the uniprocessor CPU, which was first invented, in which there is an input device which transfers the information to the control unit, and the control unit registers each and everything to the processor and tries to implement in the combination logic. If it is a logical problem, then the data goes to the combination and logic box, and if it is an on-off function, then it goes to the register, and according to that it saves the data in the main memory and implementing each and everything instruction, and it gives the output to the output devices. Next slide, please. One of the most important part of the CPU is the control unit. The control unit is the component of the CPU that directs the operation of the processor. It selects and retrieves instruction from the main memory in a proper sequence and interprets them so as to activate the other function elements of the system at the appropriate moment to perform their respective operations. All input data are transferred via the main memory to the arithmetic and logic unit for the processing. It directs the operation of the other units by providing timing control signals. Most computer resources are managed by the CPU. It directs the flow data between the CPU and the other devices. So you can understand that one of the most important part of the CPU is the control unit. Without it, no data transfer can take place, and the CPU cannot perform in the sequential manner. Next slide, please. The other most important part of the CPU is the arithmetic and logic unit. The ALU performs simple addition, subtraction, multiplication, division, and all the logical operations based on which the CPU works, such as the OR and the AND gate. Everyone knows about that. The memory stores the program instruction and the data. The control unit fetches data from the instruction from memory and uses the operation of the ALU to carry out those instructions using the data. When an input or output instruction is encountered, the control unit transfers the data between the memory and the designated I/O controller. The operational speed of the CPU primarily determines the speed of the computer as a whole. Depending on the instruction being executed, the operands may come from internal CPU registers or external memory, or the may constraint generated by the ALU itself. Next slide, please. The address generation unit. The address generation unit, sometimes also called as address computation unit ACU, is the execution unit inside the CPU that calculates addresses used by the CPU to access main memory. It is an execution inside the CPU that calculates addresses used by the CPU to access main memory by having address calculation handled by the separate circuitry that operates in the parallel with the rest of the CPU. The number of CPU cycles required for executing various machine instructions can be reduced, bringing performance and improvements. While performing various operations, CPU need to calculate memory addresses required for fetching data from the memory. For example, in memory, positions of the array elements must be calculated before the CPU can fetch data from the actual memory location. Next slide, please. One of the most important part is the memory management unit, because each and everything is stored over here. A memory management unit, MMU, sometimes called page memory management unit, PMMU, is a computer hardware unit. You can see the picture. Having all the memory references pass through itself, primarily performing the translation of virtual memory addresses to physical addresses. The memory management unit is a hardware component which is a part of the CPU. When the MMU is enabled, the CPU accesses memory via virtual addresses which will be translated by the MMU to physical addresses before sending them on the memory bus. Every CPU has its own MMU. Modern MMUs typically divide into virtual address space into pages, each having a size which is a power of 2, usually a few kilobytes each KB, but they may be much larger. The bottom bits of the addresses are left unchanged. The upper addresses bits a virtual page and numbers. Next slide, please. The clock rate, the most important thing, the clock rate. The clock rate is the speed of data transferred by the CPU, or you can say the most CPU has synchronous circuits, which means they employ a clock signal to pace their sequential operation. The rate measures the number of cycles a CPU executes per second, generally measured in gigahertz. A CPU with clock speed of 3.2 gigahertz executes 3.2 billion cycles per second. As of 2014, the Guinness World Record for the highest CPU clock rate is an overclocked 8.723 gigahertz AMD pile driver based FX8370 chip. To ensure proper operation of the CPU, the clock period is longer than the maximum time needed for all signals to propagate through the CPU. In setting the clock period to value well above the worst case propagation delay, it is possible to design the entire CPU and the way it moves data around the edges of the rising and falling clock signals. Next slide, please. So here is the evolution of the CPU processor, where you can see the first processor was developed in 1971. And can you believe, guys, the first processor had a clock rate of 5 to 10 hertz, only hertz, and now we have reached a speed of 8.723. We have covered a long idea to improve our processor so that we can have a better control on the computer and we can work faster as compared to the others. Next slide, please. Now this is one of the most important thing which I thought that I must discuss with you all or must explain to you all. It is a Neuralink. Now there are many students who may know about the Neuralink and many other who doesn't know that what a Neuralink is. So let me give you a brief detail about a Neuralink. So a Neuralink is I can say that this is the next generation, or you can say it is the future of the computers. Like what if I say that your brain starts to function as a hard disk? Means you can learn any skill which you want just by data transfer from a computer to your brain. Sounds interesting. So this is possible by a company which is developed by the Elon Musk, one of the greatest future entrepreneur, who has developed this technology of Neuralink. The Neuralink is one of the most important thing which I think in future it will help us to cooperate with the modern AI, which is having a great intelligence day by day. If we in the Neuralink, a thought of the entrepreneur Elon Musk, it is a kind of technology that will connect human brain with a computer brain or the CPU, or we can say human brain and a computer interface. It will allow to human give input to the computer without even touching a hardware. Now it has some disadvantages also, like if this kind of thing happens, then there will be many disadvantages of misusing and many things. So that's why this is an topic which is going on and the government has not legally approved it, but I think when the topic will be approved, this is one of the greatest revolution in the human mankind. Thank you very much for listening to me. Now my next companion will explain the next topic. Thank you.
Thanks, Abhishek. Nishant, can you go to the assembly language slide once? Yeah, just this one. Yeah, so I just wanted to give one information. This picture that you see is one of the first architectures that were given. It is called the von Neumann architecture. It was given by John von Neumann in I think 1940s. He's one of the most popular scientists. He also is the father of game theory, a field in mathematics. So yeah, Nishant, can you go to pipelining now? Let's look at the first. So you're at McDonald's or let's say any drive-through, and you're second in line. And there are 3 stages for you to complete the process. So one is where you place the order, then one is where you pay, and then there is lastly where you collect the order from. Now let's assume each stage is taking you 3 minutes. And now as soon as the first car leaves, that's when your time begins. So it's going to take you now entire, if you look at it, 12 minutes, because your time starts as soon as the first car leaves. So usually what happens is that we think that as soon as the person leaves the ordering counter, we would be next. But what if someone stops you? So you're it's not 9, it's your 12-minute process is now going to turn into 18-minute process. And the next person's, the third person in line is gonna have to wait now 27 minutes, and so does the series go on. Now this is hazardous because time is important firstly, and this is not efficient in any ways. So pipelining is a solution to this. Pipelining is an implementation technique where there are multiple instructions that would be happening at the same time. They would be executed at the same time. So there's a concept called parallelism. Pipelining takes advantage of it by implementing all the instructions at the same particular time. Pipelining so there are majorly two ways that we can improve CPU speed, or to make them faster. Pipelining is the more efficient one. We look why is that in a time, and now pipelining is nearly universal, and it is the key technique to make CPUs faster. Can we go to the next slide? Yeah. So it was pretty obvious that it is not efficient to wait that long in the line to get your order. As I said, it's not what exactly happens, and there are multiple steps that there are multiple instructions that happen in real life. Like as soon as the person leaves the place your order counter, we go next. As soon as he leaves the pay your cash, then we go there. So simultaneously everything is happening. So this is an example of pipelining, and you can observe this almost everywhere, majorly in production systems. If we manufacture one unit at a time, like if we need to manufacture, let's say, an automobile, if we put the entire day in making one automobile, just one car, is going to be really, we'll end up in a loss. So now, why pipelining? So there are two ways to improve the performance of CPU. One is that we improve the hardware, and that is by making the circuits faster. And then it is to arrange the hardware in such a way that more instructions, more operations can be performed at the same time. Now, the first option, though, has come a long way. We have faster circuits available, but they still remain very expensive, not available to all. And there's always a speed limit on hardware. So that's why pipeline has become universal. Pipeline is, in a way, philosophical too, because it can be applied to almost anything. So that way, CPUs now mainly run on this principle, which is pipelining. Can we go to the next slide? Yeah, so this is a visual representation of why overlapping of instructions can be helpful. As you can see in the non-overlapping cycle, so S1, S2, S3, S4 are stages, and one stage, okay, so the cycles. So if you look at the instruction one, every instruction takes 4 stages. So if we go by the method that was hypothetically being done in McDonald's, it's going to take you 8 cycles for 2 instructions to execute. But if we overlap the instructions, it's going to be more efficient. This can actually be achieved in far less than, actually even lesser than 5, if executed properly. We can go to the next slide. Yeah, so the basic design of a pipeline involves input and the output end, and stages in between these two ends, and one output serves as the input to another stage, and this is how the entire thing propagates. Then there are registers, registers actually hold the result of a particular stage. So if we in the process, let's say in process 3, there's a result that we need to store for, let's say, process 4 or even 5 or later processes. Interface registers would store that result, and this would create a buffer too at the end. So that's why these registers are called buffer. And all these stages in the pipeline, along with the interface registers, are controlled by a common clock. We can go to the next slide now. Yeah, so of course there are a lot of hazards. Pipeline, as you can imagine, as a usual pipeline, there can be blockages, there can be various issues that can be there. So these are called hazards that prevent the next instruction to be executed during a cycle. So, and they cost a lot as they halt the process, so we don't have a speed up gain. And there are mainly 3 hazards. So the first is structural hazard, which rises from resource conflicts, and that can be said like two instructions are competing for one particular asset, one particular system, and so there's a conflict between which instruction gets it. And yeah, so of course the hardware cannot support all the combination of instructions simultaneously in an overlapped execution. Then there are data hazards, when an instruction depends on the result of the previous instruction. So it can be also said that sometimes there are issues which rise in processes. So if one particular step gives wrong data, then it's going to create then the next entire process might be faulty. So this is an example of data hazard. And then the last one is control hazards, which arise from the pipelining of branches that change the PC. A way to counter these is by stalling the pipeline. So avoiding a hazard often requires that some instruction in the pipeline be allowed to program while others are delayed. So stalling basically means that we halt the process so that there is no blockage. Divide in a proper later. So stalling is that it's stopping the process for a while so that everyone gets what they want. Yeah, we can go to the next topic now.
Yeah, hello, good morning, guys. This is Sai Ganesh. I'll be explaining you about memory systems. So whenever we dive into any topic related to a computer field, the most important thing that we require is data. So let's say you are working on artificial intelligence or machine learning or any other stream. The very fundamental requirement is data with which we are going to come up with conclusions. So storing such important data is called memory. So this is what we'll be seeing into today. As this topic is very brief on its own, I'll be just briefing you about it. So first thing what we'll be seeing is the types of memory. First is I'll be coming with first is cache memory, which is the very fastest memory as of now. Though the memory system is completely continuously developing, as of now the fastest memory that we have is cache. And the second fastest memory is main memory, which is DRAM. This is we have two different things in it. The cache is generally made with SRAM, and the main memory is DRAM. The SRAM stands for static random access memory, and DRAM stands for dynamic random access memory. So the last thing is virtual memory, which is similar to the hard disk, where we have a lot of our informations. So the difference stands here. Cache memory is the fastest memory, the SRAM. It is so fast because it has 6 transistors inbuilt in it. 6 transistors for 1 bit of memory, where the dynamic RAM has only 1 transistors for 1 bit of memory. So you could see the cache memory is so fast, but it is also very expensive. So though people could question why can't we have only cache memory, the fastest memory SRAM in our PC, but the problem is it is very expensive. So memory system and memory organization is in which we do a best optimization method to have a best source of memory with a cheaper cost, cost efficient, and with a good speed. Nishant, can you move to the next slide? Yeah. So in memory organization, the most optimal method for having a cost efficient memory and a very quick memory is this, the diagram that is shown here. That is, you will be having 2 different cache memory, that is 2 different static random access memories. That is, one is cache and is cache. Very very small size, that is you would be having only around some 500 MB. The main memory would be that's the RAM, and you would have some 4 GB of something, and hard disk is the way you have the most of the information. This memory organization works in a way we know that CPU could only interact with the most fastest memory because CPU is very fast. When CPU straight away comes in contact with hard disk, it takes very lot of time. I mean, it is no way efficient because it takes a lot of time. So CPU generally interacts only with cache. So in order to increase the speed, what happens is whenever we are in search of some information, memory from hard disk goes into main memory and then it goes into cache memory and then it goes into CPU. So this is the way we speed up the memory system. Nishant. Okay. So this cache memory is a way in which like we have the most important thing that is usually searched for in it. Let's say like you often open PowerPoint in your PC, and that particular PowerPoint would be always in your cache because it is often open. So informations that are always prompted for stays in cache memory because it is very quick in nature. So this cache memory works on two important factors. First is temporal locality, that is it depends on time. Let us say, as I gave you an example already, let us say you are working on a code that is always used for let's say in the way like yeah, as I told you, let's say you have a software that you are opening often. So as it is working on time t, it is very likely to be working on some t plus x. So such informations are always stored in cache. The next is spatial locality, that is working in a factor of space. That is, let's say you have an array of code. You have an array. Let us say you are working on array some like 15th array. So if you are working on 15th array, it is very likely that you will be having the most nearest, the most proximum array within it. Like you will be working on 16, 17 and all those things. So such a space bound array informations are also put on cache. So this is the way the cache is fundamentally divided into. Nishant? Yeah. So when it comes to memory hierarchy systems, we have some very fundamental quantities. First one is hit. That is the probability. Hit is always referred to the most proximum memory, that is cache memory as of now, because that is the only memory that is very close to the processor. So hit will be like the probability of finding the prompted information in the cache memory. Let us say you prompt for some variable x. If that way, the probability of finding the information of variable x in the cache memory is hit. Miss is when you can't find the memory in a required disk. Hit rate is, yeah, it is so similar to the hit, and miss rate is also the probability of finding not. So Nishant. Okay. So we'll be calculating the effective time formula because when it comes to memory, all we bother about is speed, because we need how speed it is most important for us. So how we calculate that depends on few factors. That is, as we saw, that is hit rate, miss rate, and the hit time and miss time. So hit time is the time that is taken to like access the memory in the cache memory, and miss time is the time taken to access the memory that is not found in cache memory. So to find the minimum time, I mean the average time required to find the prompted information, we'll calculate in such a way that like it is the hit rate into hit time, that is time taken plus the miss rate. That is like, let's say you prompt for a variable x. Again, the same example. In this, what you do is the probability of finding the x is hit rate, as we know, and the time taken to take from it is hit time. So that average time, if it is found in cache memory, is hit time into hit rate, and if it is not found in it, we take it as miss time into miss rate. Nishant? I'll move to next slide. Yeah, okay, thank you. So in this you could see that when it is not found in cache memory, we have other probabilities. That is like it would be found on the secondary or the next level of memory. So we take it as like the memory, the time taken to back the memory, the secondary, and to prompt it again for the required information. So this information. So the total average time taken is given by the formula like hit time into hit time plus miss time into the hit time plus miss rate plus miss penalty. So this this simple formula could also be extended for memories with many number of disks. And yeah, that's it. Now my friend Vimalesan will be explaining you on bus systems.
So go to the next slide. So a bus system is like a path for the data to transmit inside any electronic system. It's like how a regular bus works in real life. Before there used to be many types of buses like an address bus, a control bus, and a data bus. Each had its own functions, and they used to be separate. But as uh, as it became as they wanted to be more cost efficient and reduce space occupied, in the 1970s and the 1980s, they started making it compact and they use printed circuit boards. Go to the next slide. So a brief history. Back in 1950 and 1960, like Ajay said in assembly language, computers could only do one function. So they were connected in that in a way that they could not do any other function other than what they wanted it to do. Like suppose if they wanted to do calculation, it wouldn't do anything else. So when the circuit boards were not yet there, they used to use back planes where the wires were just bundled and connected to each box of a CPU, a memory, and an input output unit. So, and then later on, when integrated circuits were more common and they were able to make printed circuit boards, they started making it smaller and it became more standardized to use a bus system that rather than connecting each component separately. Next slide. So these are the components. This is a control bus. In the picture you can see the control bus, address bus, and the data bus. The address bus determines the address of where it should be sent, and the control bus determines the operation, and the data bus carries the information. So the address line is used to carry address to the memory and the I/O, and it is unidirectional as seen in the picture. And determined based on this width of the address bus, you can tell about the capacity of the main memory. And then the data lines, these are used to carry binary data between the CPU and the memory and the I/O. It is bidirectional, and based on this width we can see the word length of the CPU, and the word length can tell about the performance of the CPU. Control lines are used to control the signals and the timing signals. This tells about the type of operation, and this timing is used to synchronize the memory and I/O operations with the CPU clock. Go to the next slide. So development of bus system, as they started making multiple bus systems they started connecting them because speed was a problem, and they they started using this thing called dual independent bus, where there were two buses connected, and one was used as a main memory and the other was used as a CPU with more than one CPU. This was first implemented by Intel in their Pentium Pro and Pentium 2 processors, and ever since 2005 they started making 4 processors in 2 bus systems, and this gave them a really fast speed like up to 12.8 GB per second. But when this happened, there was a lot of cache information that was going to waste. So they wanted to use it up. So they made this thing called Snoop filters, which cache the Snoop information, which is the information that was being lost. Modern computers still have improved on this technology using things like hypertransport and Intel's quick path interconnect. And even now we can see the system bus architecture used in embedded microprocessors. And that's it. Modi will do the next one. IO interface.
Thanks, Vimal. So IO interface is basically that there are external and internal. So there are external devices like keyboard, printer, and there is internal storage. So there has to be transfer of information between them, and the method that is used for the transfer is called IO interface. And just a second. So there can be special links with the peripherals. Now, when peripherals basically mean the external input output devices, and the binary information. Go to the previous slide. Yeah, so the binary information that is received from the external device, like mouse, is stored in the memory unit. To the external device is also originated from the memory unit, and the CPU is merely processing the information, but the source and the target is always the memory unit. And data transfer between these CPU and input output devices has basically three different modes, and those are programmed input output, and interrupt initiated input output, and direct memory access. We can go to the next slide. Yeah, so each data item is transfer is initiated by an instruction that is there in the program. So usually the transfer is from the CPU register and memory, but in this case it requires constant monitoring by the CPU. So there is an active responsibility of the CPU, and in this case the input output device does not have a direct access to the memory, so it can't directly communicate with the memory unit. And in programmed input output, the CPU stays in the program loop, like it's always on, and indicates that the input output unit is ready for data transfer. And this, as you can possibly imagine, this is time consuming, as CPU takes a lot of, is constantly running, and this can be avoided to a good extent by interrupt initiated input output. Next slide. Yeah, so in the above case, the CPU was kept busy unnecessarily the whole time. The situation can be avoided by this interrupt method for data transfer. And in this interrupt facility, there are and special commands inform the interface to issue an interrupt, and wherever the data is available for any device. So it would send an interrupt whenever there's a signal that's received that this device is available for data transfer now. And in the meantime, the CPU can proceed for any other program execution. The interface will keep on monitoring the device, and whenever it is determined that the device is ready for data transfer, it initiates an interrupt again and request to the signal. And upon detection of an external interrupt signal, the CPU stops momentarily the task that it was already performing, and branches to the service programs to process the input-output transfer and then return to the task that it was originally performing. Next slide. Yeah, so these two methods require the intervention of the CPU, the processor, to transfer the data between memory and input-output devices, and these data transfer must traverse through an entire pathway through the processor. So there are two drawbacks. The input output transfer is limited again by the speed of transfer, which we saw in the pipeline, and the processor is tied up in an input output transfer. A number of executions must be executed for each transfer, so it gets complex. Next slide. Yeah, so suppose any device is connected at an input output port and wants to transfer data to any other to the memory. So first of all, it would send input output port address, control signal, input output read to input output port. It would send memory address and memory write signal to memory data where it has to be transferred. So this technique is quite busy, as we have seen in the previous two, where any input-output operation is completed or not for next input-output operation. Therefore, this technique was slow. This problem of slow data transfer between input-output port and memory between the two memories is avoided by DMA, which is direct memory access. And we can go to the next slide. Yeah, so direct memory access the data transfer between a fast storage media such as magnetic disk or a keyboard or anything, and memory unit is limited by the speed of the CPU. Thus, we can, if we remove the CPU and directly access the memory unit, we can achieve faster speed. So we can allow the peripherals to directly communicate with the memory buses, removing the intervention by the CPU. And this is the direct memory access method. And yeah, we can go to the next slide. Yeah, so DMAC 8257 is an Intel core, is manufactured by Intel, and it is used for the fastest rate to data transfer. So what happens is the input output device sends a request, and then the DMAC sends a hold request to CPU. The CPU acknowledges that hold request and sends it back. Then the DMAC acknowledges that hold request and sends it to input output interface, and then the entire process starts where it is where the input output device is allowed to read or write, and it is done through buses, as you can see, A bus, D bus, and C bus. Next slide. Yeah, so an important topic is input output processor, and so the DMA mode of data transfer reduces CPU's overhead in handling operations. It also allows parallelism. Such parallelism is necessary to avoid wastage of valuable CPU time while handling input output devices whose speed are much lower as compared to CPU. The concept of DMA operation can be extended to relieve the CPU from extensive involvement in execution of the input output operation. So this is why we introduce a special processor called input output processor, and it is just like a CPU that handles the details of the operation of the input output. It is more equipped with facilities, and it fetches and executes its own instructions that are specifically designed to characterize input output transfers in addition to the input output related tasks, and it can perform various tasks like arithmetic logic, branching, and code translation. Yeah, we can go to the next slide. Yeah, so this is just a diagram of the input output processor. Next slide. Yeah, so the major advantages of input output processor is that the input output devices can directly access the main memory without the intervention by the processor and input output processor based systems. It is used to address the problems that rise in the direct DMA method. Next slide. Yeah, so bus arbitration refers to the process by which the current bus master. So bus master is the one that has the access of bus at an instance. So it controls the access to the current bus and then leaves the control of the bus and passes it to another bus requesting processor unit. And the conflicts may arise in this as there can be multiple instructions asking for the bus. And this is where different methods have evolved which can be used. And we'll look in the one in the next slide. Nishant, next slide. Nishant.
Daisy chain method, eh?
Yeah.
Yes,
Daisy. Yeah, it came now. So it is a simple and.
Do you have the 11:30 classes? Do you have classes, or we continue the session and?
So it'll take just 1 minute, so it's over.
Okay. If you don't have any other problem, we can conclude as per your presentation.
So in daisy chain method, the conflict is solved by allocating it hierarchically. So device 1 gets the first preference for bus request, and after its process is done, it gets transferred to device 2 after device, and this goes on. So the first master or the first device that has access is device 1, and this follows and it solves the issues. Yeah, so we're done.
So we're done.
Have you completed all the slides?
Yeah.
Yes.
Yes, sir.
Yes. I have some doubts. And can you please elaborate? Do you have any idea about the microcontroller and ladder diagram and PLC? Microcontroller, ladder diagram, and PLC. Do you have any idea?
Sir, can you specify under which topic it comes, because we
that we have revealed, and it was also an evolution over the advancement of the computers, that is microcontroller and then ladder diagram and then PLC. Do you have any idea?
So microcontrollers are like, they include all the things like the memory, CPU, and input output in the same chip.
Okay. Where we are using PLCs?
So like microcontrollers, so like the microcontrollers and microprocessors, the microcontrollers have a ROM, and the other peripherals along with the CPU and the processor. Means it is a current next generation CPU which involves a small chip, the microprocessor attached to the CPU, like the Intel Gen and each and every one. So if you need a large amount of really fast memory, then microprocessor is likely your best option, sir. A microcontroller is already the choice of very fewer than within a microprocessor. The maximum amount of flash memory available with most of the microcontrollers usually is around 2 MB.
Yes, very good. And it is feasible to make the computers to understand the differentiation and integration. Computer can understand differentiation and integration without the aid of any software.
Yes, sir. Actually, in MATLAB, we have specified codes for doing differentiation and integration.
Yes. Very good. Till the development of MATLAB, we are unable to make the computers to understand the differentiation and integration. And someone touched about the solving procedure of physical phenomena. That is quite possible by the application of MATLAB. MATLAB, with the aid of MATLAB, we can solve the integration and differentiation. And my appreciations to each and everyone, Nishant, Maharajan, Ajay, given a very nice. You have collected such information, very detailed information.
So we used Wikipedia and then Google Scholar. There were articles.
Google Scholar.
So there's a site called Geeks for Geeks. There was a very good material there too.
Little louder. Which site, Anand Modi?
Geeks for Geeks.
Geeks. GEES.
GEEKS. Geek for Geeks.
Very good. My appreciation to everyone. You have given a very detailed presentation. Still, we are in referring to your text. It was very old in syllabus called binary numbers, sequence and series, binary fractions, binary shifting, scientific notations, machine numbers, computer accuracy, computer floating point numbers, and Hoffman revealed the programs significant digits, precision, accuracy, errors, and number representation. But it was little advanced. You made, I think you made a benchmark for others to present their presentation. We will see what others will do. It is an attempt made by you. It was a very good attempt. They have to complete the presentation which was made by the today's presentation, and it was very good. As said by former President Pranab Mukherjee, always worried about the colleges which is situated in India. In top 100 colleges, in top 100 universities, we don't have a single colleges is still even we have NITs and IITs, IASs, and we don't have a single college in top 10, top 100 in the world. Like that, he always shared his sadness towards the education. But he also insisted that we are 20 years far behind than the developed countries. But I think you are given a very detailed information that when if we have Pranab Mukherjee, I won't accept you are far ahead. My appreciations, and I request all others to present in such a way. Like the today's presentation, I request all others to give a very detailed and very nice presentation. Thank you. Tomorrow we'll meet. Do you wish to share anything?
Sir, actually the class timing is over.
Yes.
So
Yes, so we have a class.
Yes, sir.
Yes. You please join the other class. Tomorrow we'll meet.
Thank you.
Okay.
Thank you, sir.